So hi and hello there. Welcome to the new video of the course. So in the previous session we saw the working and the designing part of NAND gate. We also saw the truth table of the NAND gate, right? So in this particular video what we are going to do, just by using the truth table of NAND gate, we are going to prove certain thing. Okay, so at the end of this particular video you would be in this situation to understand one law. I'm not taking the name of that particular law. Okay, so without wasting any further time, we'll straight away jump to the today's sessions. Okay, so let me just write the inputs and let me just deduce certain things out of this particular tabular form or this particular truth table. Okay, so the inputs were a and b, right? A and b, right? These were the inputs for the NAND gates. Okay, as we all know, NAND gates has two inputs. If you don't know, let's just revise the things that we had studied in the previous session. So as you can see over here, this is your NAND gate and it has two inputs. This is first and this is second, right? Great. And this was the truth table of NAND gate. Okay, so let me proceed further. All right, so this is your two inputs a and b. So now what I'm going to do, I'm just going to take the a bar and b bar, right? So what I'm going to do, I'm just going to provide one NOT gate in front of this particular two inputs, right? A bar and b bar. Okay, and then what I'm going to do, I'm just going to multiply these two, that is a into b. Great. And then what I'm going to do, I'm just going to take negation of this. Okay, a into b the whole bar, that is I'm just inverting this particular input. And the other thing that I would like to do over here is that let me add these two particular inputs, that is a bar plus b bar, a bar plus b bar. So for this we obviously we require OR gate. Okay, that's a different scenario, but let me conclude certain thing out of here. Okay, so we all know what is the input that we are providing to the NAND gate. Okay, that is 0 0 0 1 1 0 and 1 1. So these are the set of inputs, okay, or four possible input combination out of these two logics, right? Great. So now what we are going to do, see, we have a as 0 0 1 1. So obviously the a bar would be 1 1 0 0 1 1 0 0. Okay, I hope you know this particular thing. What we had done, we had done nothing. See, if this is a NOT gate, I hope you know this particular thing, but still it's my responsibility to explain you each and everything in depth. So if this is a, so let's suppose your a is 0, so your a bar would be 1. So this is what we had done over here. On the similar note, if your a is 1 over here at the input side, so a bar would be 0. Okay, and this is what we had done. So if it is 0, so a bar would be 1. If the a is 1, so a bar would be 0. Okay, I hope you understood this particular thing. Let me erase it. Okay, and now same goes with b as well. So b is 0 1 0 1, so b bar would be 1 0 1 0, right? 1 0 1 and 0. Okay, just inversion of b. Okay, and then what we need to do, we just need to multiply these two logics. Okay, that is the inputs that we are feeding, that is a into b. Obviously this can be done with the help of AND gate, which we had seen in the previous sessions as well. Okay, so 0 into 0 is anyhow 0, 0 into 1, anything multiplied with 0 is 0. Similarly over anything multiplied with 0 is 0. Great. And 1 into 1 is 1. Okay, now uh, we have to take negation of this particular set of logic. So a into b is 0 0 0 and 1, three zeros and 1. So obviously when I'm giving or fetching this particular input to the NOT gate, so it would be 1 1 1 and 0, right? So it would be a into b bar would be 1 1. This would also be 1. Just a second, let me align it properly. This is 1, this is also 1, and this is also 1, but this would be 0. Okay, this is what we had seen in the previous session. This was the truth table of the NAND gate. So as you can see over here, this is the truth table of NAND gate. A b bar, as you can see, 1 1 1 and 0, right? So this is what we had done over here. Now see, now what I'm going to do, I'm just going to add these two, that is a bar plus b bar. So we all know 1 plus 1 in digital electronics, 1 plus 1 is nothing but 1 only. Okay, that is 1. Okay, this we had discussed in depth during OR gate, during the concept of OR gate. Okay, if you remember, the LED was glowing brighter as compared to the previous cases when we were giving input as 1 0 or 0 1. Okay, so if you compare that cases with 1 1, so LED was glowing brighter in this particular scenario. Okay, but uh, as of now we are not building with the OR gate. Exactly, we are just what we are doing, we are just adding, or basically we are just providing one OR gate uh, uh, to this particular input, right? A bar plus B bar. Okay, so A bar is 1, B bar is also 1. When you add them you get 1. Then your A bar is 1, B bar is 0. Anyhow, since you are adding it, so it would be 1 only, right? Over here as well, this 0 plus 1 is nothing but 1. Great. But over here if you could see, A bar is 0 and even B bar is also 0, so the answer would be 0. Okay, so now I hope you might have noticed this particular thing. Just see over here clearly. See these outputs, A into B the whole bar and A bar plus B bar. What you can say is that, see the logic that we had got, 1 1 1 1 1 1 and 0 0. So this is the truth table for A into B the whole bar, and the truth table for A bar plus B bar. It is exactly similar. So from this particular truth table, what I can conclude is A bar plus B bar is equivalent to A into B the bar, A into B the whole bar. So this is the thing that we need to conclude, and it is A into B the whole bar, A into B the whole bar is equivalent to A bar plus B bar. So this is the first rule of DeMorgan's law. So this is what this is a DeMorgan's law. Okay, let me just highlight it, and this is the first rule of DeMorgan's law. First rule of DeMorgan's law. So this is first rule of DeMorgan's law. First rule of DeMorgan's law. DeMorgan's law. Okay, there is another rule. So combinedly, just by combining both the rules, we like both, when we combine both of the rules, we combinedly term it as DeMorgan's law. But this is the first rule of the DeMorgan's law, wherein what we had done, we can convert the NAND gate into OR gate just by connecting one NOT gate to both of these inputs, right? I hope you're getting my point. So see, just a second, let me add one more page over here. Just a second. Yeah, so what we were doing traditionally was this. See, in case of NAND gate, so let's suppose this is your NAND gate, right? NAND gate. So how you were supposed to draw on one NAND gate? So obviously what you were doing, you were providing these two inputs to one AND gate. Okay, so this is your, let's suppose this is your AND gate, and whatever the output that you were getting, you are feeding it to NOT gate. So this is a NOT gate. Great. And this is your output. So if the input is AB, right, over here you were supposed to get value of AND gate as A into B, right? And when you are passing it through NOT gate, so it would be A into B the whole bar, right? On contrary, you can also design this particular NAND gate in this way, that is, oh sorry, just a second, let me write it properly. So this is A into B the whole bar. Now if you want to draw not NAND gate, one NAND gate, you can also draw it in this way, that is, see, A bar plus B bar. You can also write it in this way, that is, let's suppose this is your one NOT gate. Okay, this is one input and this is another NOT gate. Okay, this is another input. Okay, and then what you are doing, you are feeding this particular output, whatever the output of this NAND a NOT gate may be, you are feeding it to one OR gate. You are feeding it to one OR gate. So this is your OR gate. This is your OR gate. I hope you know the symbol of OR gate. Now by now you might be very much well acquainted with the logic gates. Okay, so this is the symbol of OR gate. Okay, this is NOT gate. So this is your A, right? This is your B. If you are providing two inputs, right, over here you would be getting A bar, over here you would be getting B bar, right? And at the end of the OR gate you are getting what? A bar plus B bar. So henceforth, maybe in the further sessions, I may also go with this particular circuit. Okay, this particular logical circuit, or I may also go with this particular logical circuit. It's up to me and it's up to the question, right? Henceforth, like if we will be solving some questions, if we are dealing with some project, so you can also go with this one, or you can also go with this one, right? It's up to you. Okay, And but remember this particular rule, or this particular first rule of De Morgan's law, it is very much important, because henceforth in the next sessions, while we will be dealing with the minimization of logic gates, we would be using this particular equation or this particular expression very rigorously. Okay, so try to remember this particular equation. It is pretty simpler. In case of multiplication, you just have to add, and you just need to separate the negation or the inversion, right? I hope you are getting my point. Okay, so video we are going to see, or basically we are going to deduce the second rule of De Morgan's law. Okay, so in the previous session we saw the concept of NOR gates, its designing part, its truth table and all. Okay, so in this particular session we are going to deduce the second rule of De Morgan's law. Okay, I hope you remember what is De Morgan's law. I mean, we had studied the first rule of De Morgan's law when we were dealing with NAND gate, right? So let me write down the inputs and certain things which are required to deduce the second rule of De Morgan's law. So obviously, we will require two inputs, that is input A and input B. Okay, then I would be taking its complement, that is A bar and B bar. And then since we are dealing with NOR gate, so I will add both of the inputs. Okay, and then I will take its complement, that is A plus B the whole bar. Okay, and then I will multiply these two, that is A bar and B bar, and then I will check what output am I getting. Okay, so we all know the inputs are 0 0 0 1 1 0 and 1 1. So these are the set of inputs. Okay, these are the set of inputs, and now as you can see, this is our A. So A bar would be 1 1 and 0 0, just complement of A. Okay, so 0, if there is 0, so here I will get 1. If there is 0, again here I will get 1. If it is 1, then 0. Again if it is 1, then it is 0. Okay, now similar case will happen with B. Okay, since we are taking the complement of B or negation of B, it's one and the same. So the values at B are 0 1 0 1, right? So B bar would be 1 0 1 0 1 0, right? Just inversion of whatever the values that are present at B. Okay, and now we need to add these two uh, values, that is A plus B, in the section of A plus B, right? So A plus B, that means 0 plus 0 is anyhow 0, 0 plus 1 is 1, 1 plus 0 is 1 again, and 1 plus 1 is again 1. Okay, great. And now we need to take its complement. Okay, that means A plus B the whole bar. That means we just need to take its take the negation of these particular values, okay, that we had obtained over here. So the negation of 0 is 1. Okay, the complement of 0 is 1, 1 is 0, 1 is 0, and again 1 is 0, right? Great. And now we need to just a second, let me write this one clearly. Alright, so now we need to multiply these two values, that is A bar and B bar. Okay, so I need to multiply A bar and B bar. So 1 into 1 is 1. Okay, 1 into 0 is 0. 0 into 1 is again, now it is 0, and 0 into 0 is 0. So as you can see over here very clearly, see over here, this A plus B the whole bar is equivalent to A bar into B bar. So this is what we are getting, right? Let me erase this thing. Yeah, so A plus B the whole bar is equivalent to A bar into B bar. So this is the second rule of what, of De Morgan's law. Okay, I hope you understood this particular rule. As such, there isn't anything to learn, just we had proved it using the truth table. Okay, and again we are going to see this particular De Morgan's law, I mean both the rules of De Morgan's law in depth during the minimization of a logical expression. So that topic we had not started. In fact, we need to cover exclusive logic gates, and then we will be starting with that particular topic, right? So at that particular time also we'll deal with this particular thing over there as well. I will try to prove this particular, what I can say, rule or theorem, whatever it may be. Okay, so let me write over here A plus B the whole bar, just a second, A plus B the whole bar, A plus B the whole bar is equivalent to A bar just a second, a bar into b bar, a bar into b bar. Okay, so this is the second rule of DeMorgan's law or DeMorgan's theorem. Okay, second rule of DeMorgan's theorem. Second rule of DeMorgan's theorem or DeMorgan's law. It's one and the same. Okay, so I hope you understood this particular law. As such, there isn't any need of understanding anything. We just wrote all of these things in the tabular form, and then we, with the help of this particular truth table, we had deduced this particular equation, right? So let me take one more page and let me add both the rules of De Morgan's law. So whenever you will refer my PDF, you should be in this particular stage to know both the theorems. So the very first theorem or the very first rule was A into B the whole bar is equivalent to A plus A bar plus B bar. Yeah, A bar plus B bar. Okay, and the second rule is A plus B the whole bar is equivalent to A bar into B bar. So as you can see over here very clearly, on the LHS side we are taking the negation on, to the whole of the term, right? So A into B the whole bar, right? And to the RHS side we are taking the complement to the single what I can say, single alphabets or the single variables, right? Single variable input. So okay, over here as well, as you can see, we are taking the complement to whole of the equation, that is A plus B the whole complement, and over here we are taking the complement or the negation sign just with a single variable. Okay, but the point to notice over here is that when you are taking complement, okay, and whole of the term is getting multiplied, so if it is A into B the whole bar, so over here at the RHS side you are getting addition, right, with single complement variable. So as you can see, A is single, B is also single, and they are complemented differently. Okay, and over here as well, if you are saying that all of the equation A plus B the whole bar, okay, when it is equivalent to the single complement of A into single complement of B. Okay, I hope you are getting my point. Okay, so how we can what I can say, yeah, how we can just a second, let me add one more page before coming to that particular point. Yeah, how we can implement the symbol, the gate of this particular equations. Okay, so as we had learned in the previous session as well, we can implement it in this way. See, the very first the very first way to implement NOR gate is this, that is OR gate followed by NOT gate, right? OR gate plus NOT gate, right? So how I am supposed to implement it? So if this is your OR gate, okay, if this is your OR gate, right? OR gate has two inputs, okay, input A and input B maybe, right? The output of the OR gate, it is fetched to the NOT gate. The output of the OR gate, it is fetched to the NOT gate. Okay, and this is how the circuit can be designed for the NOR gate. So if these are your two inputs, that is input A, input B, so obviously here you will get addition of both the inputs, so A plus B, okay, and since we are passing it with the NOT gate, so obviously your output would be, that is Y is equivalent to A plus B the whole bar. If you don't want to design this particular or implement this particular what I can say, logic gate in this way, okay, or the logic with this logic of this particular gate in this way, so you can also go with this way, with the help of this expression, that is, we all know that A plus B the whole bar can also be written as A bar into B bar. Great. So you can also go in this way, that is, see, first you need to take a NOT gate. Okay, so let's suppose if this is your NOT gate, okay, and you have to take another NOT gate, and then you have to fetch both the inputs to the AND gate. to fetch both the inputs to the AND gate. Just a second, let me write it properly. Sorry, let me draw it properly. Okay, so this is your AND gate, and over here you are taking the output. These are the two sets of inputs. That is, this is your input A, input B, and this is your Y, right? So this is your input A, right? This is your input B, and this is your output Y. Okay, output Y. Over here, at the end of this NOT gate, or at the output side of the NOT gate, you will get A bar. Over here you will get B bar, and then just a second, and then what is going to happen? Then you are multiplying both of these particular inputs. Okay, I mean with the help of AND gate, you are feeding this input to the AND gates, and then at the output side you are getting A bar into B bar, A bar into B bar. Right, great. So there are two ways or the two methods to implement NOR gate, right? So the very first method is by going traditionally by connecting OR gate to the NOT gate. Okay, or else what you can do, you can take two NOT gates, okay, and then the whatever the output that is coming from these two NOT gates, okay, you can feed it to the AND gate. Okay, so there are two ways to implement the NOR logic circuit or the NOR circuit. Okay, I hope you understood this particular point. Okay, again we'll quickly revise the things that we had studied. See, we had taken two inputs, and then we had taken its complement, and then we had added the inputs, and again we had taken the complement of this addition, and then whatever the complement that we had taken, I mean the single complement of the single variable function, so that is A, we had taken A bar and B bar. Okay, we had multiplied those two, and then what we saw is that the addition, I mean A plus B the whole bar is equivalent to A bar into B bar, right? So this was the second rule of DeMorgan's law. Okay, again I'm telling to you, we will study this particular concept in depth during the minimization of logical expression. Over here, just to clear that how exactly A plus B the whole bar is equivalent to A bar into B bar, because in in further videos we would be using it very rigorously. Okay, so just to make sure that you are very much well aware with this particular concept, I had explained this as early as possible. Okay, so yeah, moving further, I just told you the two laws. Okay, that two rules of DeMorgan's law, that is A into B the whole bar is equivalent to A bar plus B bar, and A plus B the whole bar is equivalent to A bar into B bar. The most important thing to notice over here is that on the LHS side we are taking the complement on whole of the term, that is A into B the whole bar, right? But on the RHS side we are taking the complement on the single variable. Okay, that is A, and then we are taking bar, then we are adding, and then we are taking the complement of B. Over here as well we are taking, C, over here on the LHS side we are taking complement on whole of the term, that is A plus B the whole bar. Okay, and which is equated to the RHS side, I mean the RHS is A bar into B bar. Again you can see that this is the single variable, and again this is single variable, and then we are taking the complement on the single variables, right? And the another thing that we should notice is that whatever the sign that is present at the LHS, so if LHS has multiplication, you have to do addition on the RHS side, right? And if LHS has addition, you have to take multiplication on RHS, right? And this is just a simple observation. All right, so then we saw that traditionally NOR gate can be implemented by using OR gate and NOT gate, right? I mean connecting the OR gate to the NOT gate, to the input of NOT gate, but we can also do it with the help of two NOT gates and one AND gate. Okay, as you can see, the input A is fetched to the NOT gate, and even input B is fetched to the NOT gate. The output from both the NOT gates, it is connected to the AND gate, right? And then we are getting Y is equivalent to A bar into B bar. Okay, so I really hope that you understood this particular concept